Assalamualaikum and hi, my name is Engku Adlina and I'm from Group 13. Today we will be presenting the effects of grinding parameters on ceramic strength analysis. To start off, our group members are Nur Aida, Shobana Mohan and me. Next, these are the things that we will cover in this project. As an introduction, an experiment was held at NIST to distinguish the effects of grinding parameters on ceramic strengths. So, the primary analysis was done by Lisa Jill, and now we are going to continue with more analysis. Okay, so this is our data of experiment, which is an independent analysis, but it is the modified part of the original dataset, where the response variable y is the mean of ceramic strength, and there are 5 factors. All of them are grinding parameters, and each of them is as shown in the slides.
Thank you for explaining the introduction part, Adlina. And hello, my name is Shobana Mohan, matrix number 152692. Let's move on to the objectives. This project is conducted to economically determine the significant grinding parameters that affect the ceramic strength. Furthermore, we wanted to come out with an efficient design which is faster to run by using only a subset of full factorial. Lastly, we wanted to find the best model to maximize the ceramic strength by manipulating the generators for this design. Moving on to the next part is the formula involved. As we can see here, contrast is given as the sum of the response values, sum of squares is equals to the contrast divided by 4, effect estimates is given as the value of contrast squared and divided by 4, and finally, percent contribution is given as sum of squares of x divided by sum of squares total multiplied by 100. Now, let me explain about the methodology. A factorial design experiment allows us to investigate the impact that various variables may have on a response. We can explore the interactions between the elements. As we know, in a full fractional factorial design, responses are assessed at all possible factor level combinations. A fractional design is one in which only a portion of the full factorial designs run are carried out by the experimenters. There are 5 factors in this project, which is also known as 2 to the power of 5. Plus, we are going to apply fractional factorial design. We suppose that a single batch of the silicon nitride is only enough to carry out 16 runs of the experiment. We have limited time to perform the experiment, and we want to identify if there is difference when the defining relation for the designs of this experiment is manipulated. Now, let me start with the 2 to the power of 5 minus 1 design with I equals to A, B, C, D, E. The table here shows the design with the defining relation I equals to A, B, C, D, E. The sign of E is obtained by multiplying the other sign values of A, B, C, and D. The ELYSIS structure of this experiment is as shown. The following table shows the summary statistics. We use this effect estimate summary obtained using Excel to measure the factor effects for this experiment, and the value of SST, which is sum of squares of total, is obtained as 210194.84294. This table shows the ANOVA table generated from Minitab, which gives us the degree of freedom, sum of squares, and mean squares value of these factors. From the values of percent contribution obtained from the summary statistics, we can conclude that factor D and factor E are significant. Plus, from the normal plot of the effect estimates shown, we can clearly see that some points do not lie near to the normal line. Thus, we can conclude that factor E and factor E are significant. Here we can see the ANOVA table for factor D and E, where it clearly shows that factor D and E are statistically significant as the p-value is less than 0.05. For the model adequacy checking, we use the normal probability plot and scatter plot of residual versus fitted value. Based on the normal probability plot, we can see that most of the points lie along the straight line. Hence, we can conclude that the normality assumption of standardized residual is met. And based on the scatter plot, we can see that the points are scattered in random order. This shows that the plot is structureless. Therefore, the assumption for constant variance is also met. For the model summary, the Minitab output shows that R squared value, which is equals to 89.82%, explains the variability of ceramic strength is near to the mean. And the regression equation of this experiment is obtained as y hat equals to 551.3 minus 102.6x4 minus 35.8x5. That's all for my part. I'll pass it to Aida. Thank you.
I will proceed with the second part of this experiment, which is the design of 2 to the power of 5 minus 2 with generators ABD and ACE. We proceed with the design table. We have the plus and minus table, and we have the run order. We have column A, B, C, D, E, and the treatment combination, and also the value of the strength from it. The summary statistics for this experiment, we have model term A, B, C, D, E, BC, and BE, and we also have the contrast, effect estimates, sum of squares, and also the percent contribution. In order to get these results, we have to use Excel, and we will use the formula given. So we get the contrast of A is 132.46, B 122.22, until we get the effect estimates, sum of squares, percent contribution. Next, we have the alias structures. So the aliases are I plus ABD plus ACE plus BCDE, A plus BD plus CE plus ABCDE, B plus AD plus CDE plus ABCE, C plus AE plus BDE plus ABCD, D plus AB plus BCE plus ACDE, E plus AC plus BCD plus ABDE, BC plus DE plus ABE plus ACD, and lastly is BE plus CD plus ABC and ADE. So we have 8 alias structure in this experiment. Next, we have the factorial regression, which is the strength versus A, B, C, D, and E. So we get the analysis of variance. We can see the value of degrees of freedom of each factor, and the sum of squares, and also the mean squares. So we use Minitab in order to get this ANOVA table. Next, we proceed with the normal plot of the effect estimates. So from Minitab, we can also generate normal plot of effect estimate of each experiment. So for this experiment, we can see that few points are lying far from the normal line, which makes it to be not adequate. So we can choose factors C, D, and E for model refining, since they lies far from the normal line. And we will do the model refining for these factors. The next one is the general linear model between strength and also factors CDE. So from the ANOVA table that we obtain by using Minitab, we can see that factors D and E are statistically significant. The p-value of D and E are 0.003 and 0.033 respectively. So we get to know that it is statistically significant since the p-value is less than 0.05. And factor C has p-value is equals to 0.181, which makes it to be not statistically significant. The next one is model adequacy checking. So from Minitab, we can also generate normal probability plot of standardized residuals and also the scatter plots. So first we take a look at the normal plot. So from this graph, we get to know that all the points are now lying near to the normal line. So we can see that these experiments are now adequate. The next one is our scatter plots. So from the scatter plot, we can also see that our scatter plot do not produce any significant pattern. So we can also see that the model is now adequate. The last one is the model summary for this experiment. So we get to know the S value is
37.8806, and the R squared value is 93.41, which is quite high actually. And then the R squared adjusted is 88.46. The R squared of predicted is 73.63%. And then we get the regression equation as shown in this slide.
Moving on to the last design, it is still the 1/4, but this time around we will use I equals to ABD equals to BCE. Therefore, the design table will be a little bit different since we use E equals to BC instead of E equals to AC as the generator. Just like the previous one, we come up with the Euler structure based on the defining relation. This is the summary statistics that we obtained from Excel calculation. So here we can see that in each column, factor D has the highest value, followed by factor E and factor C. The percent contribution for factor D is 76.3, factor E is 10.4, and factor C is 6.8. Then we run the factorial regression analysis in Minitab. This will help us to verify the calculation we did in Excel earlier by looking at the sum of squares value. We also obtain the normal plot of the effect estimates from the analysis. Here we can see that all of them are actually lying away from the straight lines, especially factor D. However, we still consider factor D, E and C considering the Excel calculation earlier so that there is no missing term in the fitted model. When we run the general linear model analysis using factor C, D and E, we can see that only factor D has p-value less than 0.05. Therefore, it is the only significant factor for this model. For the model adequacy checking, we observe the normal probability plot and the scattered plots for the standardized residuals. In the first plot, we can see that most of the points are lying close to the line and the pattern is following normal distribution. While in the second plot, we can see that the points are scattered randomly and there is no specific or obvious pattern. Therefore, we can say that no model assumption is violated, so the model can be considered as adequate. Finally, this is the model summary with the R squared equals to 93.50%, and besides that is shown the regression equation for the ceramic strength in this model.
In conclusions, we can see that experiment 1 and 2 have the same significant factors, which are factor D and factor E, and experiment 3 have only factor D as their significant factor, and the R square values for experiment 1 is 89.92%, experiment 2 is 93.41%, and experiment 3 is 93.53%. From the R square value, we can see that experiment 3 have the highest R value among the experiments, but we still cannot conclude the final results. By looking at the normal probability plot of each experiment, we can see that all the points are lying near to the normal line in each experiment. However, when we look at the experiment 3's normal probability plot, we can see that it has the best normal probability plot because all the points are lying near to the normal line. So we can say that factor D direction has the highest effect on the ceramic strength, and we managed to save the cost and time of experiment by using the fractional factorial design, and then we can conclude that the best model to maximize the ceramic strength is the third model. So that's all from our group. Thank you.